Hello, we're going to be covering chapter 24 today. So we're going to be dealing with the Diels-Alder reaction for making six-membered rings and oxidative cleavage. To break out alkenes and alkynes apart. So the Diels-Alder reaction is kind of an interesting one, where you come in there. It's what's called a 4+2 cycloaddition. In that you have a 4-carbon piece plus a 2-carbon piece coming together to make a six-membered ring. So you're always going to have this diene here. The two double bonds here, and then at least an alkene here. But you can also get an alkyne here. And what's going to happen is the one of these double bonds here is going to make this new carbon-carbon bond here. This double bond, that double bond there is going to make this new carbon-carbon bond, and then this other double bond is going to shift actually up here to make the alkene. So you make a cyclohexene. So this is concerted. It's a concerted reaction. Meaning that it happens all in one step. So there aren't any intermediates in this. And so what's going to happen is when you make this, right? One of the driving forces is the fact that you're making these new carbon-carbon bonds, and that looks a lot like a benzene, right? Six-membered ring, right? Alternating double, single, double, single, double, single around. So you have this benzene-like transition state. But it all comes together. So the implication for that is that a lot of these groups can't necessarily move around. So they're going to go either one way or the other, and they're going to shift together. One of the things that has to happen is this: is that the diene here, that needs to be in this what's called the S-cis conformation. It has to be like this in order to be able to attach into the what's called the dienophile to make the six-membered ring. If one of these carbons is pointed the wrong way, it can't reach over and grab this. Now, this particular molecule has the ability to rotate through this single bond here. The problem is if it's locked like this, okay, there's no way that it can go that can make that S-cis conformation. Same thing with this. So even though you can get rotation around this double bond or this single bond here to get it into the S-cis conformation, the problem is the sterics of having those two methyl groups, banging into each other. Okay, is going to keep it in this configuration here, stuff like that. And so it's going to be it's going to happen almost no percentage of the time. It's going to be negligible in this conformation. So it basically won't react. Okay. Conversely, if it's locked in the S-cis conformation, okay, so like this cyclopentadiene here, okay, this is going to react incredibly quickly, right? So we're going to make this, right? So now one of the things to note is that we are making this six-membered ring here, but this CH2 group here, okay, is going to have to get out of the way. Okay, we're not going to break it, so it's still there. So it's coming out, and it's this CH2 here is that CH2, which is that CH2. Okay, and it's what's called, because it's going from one side of the ring to the other, it's called a bridgehead carbon, and you can have either one or two carbon bridgeheads. Presumably you can have more, but that's usually the common ones for this level of Diels-Alder reactions. Okay, So again, you can have these, six-membered ring right here. So you're making So here's the diene here and the S-cis conformation. These two carbons here have to get out of the way, so we can make the six-membered ring here. So these 4 carbons, right, are these 4 carbons here. These 2 blue carbons are these 2 over here. So that's what's making the six-membered ring. And these 2 carbons here are just getting out of the way, and so they make the bridgehead right there. Do notice that this here, this acetylene group, right? So it's an alkyne. So we only need one of those pi bonds here to make the to make this new bond here. We're not doing anything to that other pi bond here, so it just remains. And so if you start with an alkyne, you end up with the alkene here, because you only need to burn one of those bonds. Okay, so with the substituent effects, what you want is, remember from the previous chapter we were talking about activating and deactivating groups. What you really want is, you really want on the diene, you really want activating groups. So things like alkyl groups, and this is fine here, stuff like that, as well as things that have lone pairs. Well, with the exception of the halogens, things that have lone pairs right next to the ring. So nitrogens, oxygens, sulfurs, things like that, that can donate electron density into these pi bonds here. Conversely, with the dienophiles, right? So this is the alkene that we're interested that the diene's going to attack with. You want electron withdrawing groups. So the classic ones are C double bond O's, right? So with that, so C triple bond N's. Nitros are going to also do that. You want this to have be very weak and allow it to be attacked. And so for here you want electron donating groups. For the dienophile you want electron withdrawing groups to speed up the reaction. Okay. Now the stereochemistry is going to be very important. Okay. So as you come in here, okay, for the dienophile, okay. So remember you're right. So let's say we have methyl groups on this side, right? So with that, and so what's going to happen is, when you make this, when you make the, when you do the mechanism here, when you make the new bonds, okay, because it's concerted, these don't have a chance to rotate around, stuff like that. And so what's going to happen is the things on this side are going to go one way, and the groups on this side are going to go the other. Okay, so with that, so since these are on the same side, we're going to say, let's say these go up. Doesn't matter which way at this point, as long as they're going the same way. Okay, so that means both of these hydrogens here, right, they're on the same side of the alkene, so they're going to point the same way. So we're going to put those as dashes. Okay. Conversely, if you had, let's say you had, the trans version of this. Okay, again, these are going to be going on one way. These are going to be going another. Okay, so if we do the mechanism, right there, there. So it's always good to draw the mechanism in, so you don't forget the double bond over here. So like that, that's an easy mistake to make. So we're going to make our cyclohexene. Now we want to say, okay, so let's say these two groups here, right? We're going to put those on wedges. That means these groups over here are going to be on dashes. They're going to go the same way, like that. Okay. So with that, so now you can get this coming in. You are going to get a mixture, an enantiomeric mixture of these two. So with that, so for my tests, you only need to draw one of them, one of the two enantiomers. Okay. So if we're looking at this, right? So with that, so right. CH3, right? So here's the diene, right? And here's the dienophile. And since these two groups are on the same side, right? So this is going to look like, so the diene is going to look like that. This group, right? It originally needs to be a double bond, but since these two groups are both on wedges, that means that they're on the same side, like that. Same thing with this one, right? Okay. Again, this is going to be the dienophile, or diene, excuse me. So it's going to looks like that. Okay. The dienophile is going to be here, right? So, right. But since notice how these are on wedges and this is on a wedge, that's on a dash. That means they're on opposite sides, like that. Okay. Okay, now there is some stereochemistry that's involved in the diene. Okay, so with that, so if it's pointed away, okay, so with that, so you usually get a if they're pointed away, they're going to be pointed in the same direction. So if they're pointed away like this, away from the double bond, they're going to be pointed in the same direction. If they're pointed inside the double bond, those two are going to be pointed in the same direction. Okay, so with that, and so. Right? So, you know, if we're just going to add these to acetylene here, or to ethylene here, you know, you're going to get there to there to there, okay? But it's these guys are going to be pointed the same way, and these inner ones are going to be pointed the same way. So when we do this reaction, right, these methyl groups are going to be pointed the same way. So let's say we're going to put those on wedges. Okay, so that means that these two hydrogens would be on dashes. Okay, they just need to be pointed the same way. Conversely with this one here, so it's not going to be very happy because of the sterics, but that's okay. So again, we're going to have that attacking there, there, there. So we don't forget the alkene here. Okay, so again, these are going to be pointed one way, right? These are going to be pointed the other. So let's say that methyl group is pointed on a wedge, right? So that means that this hydrogen is on a wedge, which means this is a dash, that's a dash, dash, dash. Okay, so that's how you're able to predict what you need to put in when you so the stereochemistry of the groups on the diene when you do the reaction. Okay. So again, on the diene, so again, notice how these two groups, right, so that are pointed inside, so they're going to point the same way. So when you do this reaction, right, so that these two groups have to be pointed the same way, right? So they're both going to be, we just said, they're both going to be on wedges. That's usually how most people write it, stuff like that, but it doesn't matter. If they were both dashes, that'd be totally fine too, stuff like that. So, but they both have to be going the same way. Okay, and the reason for that is because it's concerted. As it's coming in, they sort of have to like pop one way or pop the other. Okay, that you don't get rotation around that bond. Okay, the bond of the dienophile, and it's still a double bond, so you cannot get rotation in there. It doesn't give it, you don't have a chance to freely rotate, and so that means it's, you know, as this is coming in, it's going to go click, and so the groups that are on this side, right, are going to go on the same way. Okay, now endo versus exo. This is a problem that comes up all the time with Diels-Alder reactions. Okay, what ends up happening is when you have a pi bond on your dienophile here, okay, what it's going to do is that's going to actually get attracted underneath, stuff like that, and so you almost exclusively get what's called the endo product, where if you have pi bonds hanging off of your dienophile here, so that they are going to go down, okay, or another way of saying it, it's going to go the opposite way of the bridgehead here. Okay, this really only makes a huge difference when it's when you have a cyclic diene, right? Because that's when things are more fixed, stuff like that. And so when you have a cyclic diene here, wherever this bridgehead goes, so let's say it goes up, that means the group with your pi bond is going to go the opposite way. So if this is going up, that has to go down. If you draw that going down, that has to go up. Okay, stuff like that. And so it actually has to do, and that's called the endo product. Okay, that has to do with the fact that you get what's called pi-pi stacking. The pi bonds on your dienophile, okay, on your diene, are going to be attracted to the pi bonds on your dienophile. Okay, so as it's coming in, it's going to want to sort of slide underneath here, and so what ends up happening is it approaches like this, and so when it clicks in, it's always going to be, you know, it's always going to click in the opposite way of the way your bridgehead is going. So if your bridgehead goes up, that means your pi bonds are going to go down. Okay, so with that, and so you're going to get the endo product. If it went the other way, they would all sort of come together. You get some steric clashes, but you wouldn't be able to get that pi-pi stacking. So they'd be pointing out this way, and it would be that's the exo product, which normally doesn't occur very much. Okay, and so if you know where one of the groups is going, you know where all of them are going. Okay, so if you have this group here, right, plus, right, so if you draw out that cyano group, okay, that right there, notice how there's pi bonds here, so that's going to want to go underneath, but since it's cyclic, it's not a big deal. So like that. So, but if you know where this group is going to go, so let's say this goes on a dash, that means these groups here are going to go on a wedge, and so, right, so that's going to go there, that's going to go there, that's going to go there. Okay, so you're going to end up with this. Okay, so let's say that cyano group is going to go on a right, so there's a CH3 group here, right? Hydrogen. Okay, so that means that this hydrogen here is also going to go on a dash, which means these two guys on this side are going to go on wedges. Oop, CH3, like that. Now I had it switched, but that's okay. That doesn't matter. Okay. Now, if we have it on a where we have a bridgehead, now it becomes a little more critical about how the orientation is. Okay, so put the hydrogen here. Again, notice that there's a pi bond here. Okay, so when we do this, okay, there to there to there, usually what I want you. I should draw that in. Usually what I want to do is I'll go ahead and make the 6-membered ring here, and then put that bridgehead. I've noticed that students seem to visualize a little better if you're looking directly above it. Okay, so these two carbons here, here, and here are right there. This dot and that dot there. Okay. Now again, this one needs to go down. Okay, since the bridgehead is coming up, the pi bond has to be going down. Okay, so that means both of these things have to be going down. CH3, like that. That means this side is going up. Okay, so you have your ethyl group here, and you have your hydrogen here. Okay, so that's your product. The bridgehead is coming up, so that means your thing with the pi bond has to be coming down. Okay, so that sets the stereochemistry for all the other groups. Okay, we're going to switch gears a little bit here and talk about cis-hydroxylation or dihydroxylation, stuff like that. And so this is a little quirk, and we'll see how this goes. Why we want to do this in a minute. But with osmium tetroxide and KMNO4, when it's cold, okay, when it's hot, we'll see what happens. What you end up doing is you end up adding OHs. Across on both sides of the double bonds, right? Remember when we had the hydroboration and oxymercuration, we put an H on one side and an OH on the other. Here we're putting on an OH on both sides, but it has to be on the same side. Okay, so that the OH is going to, because what ends up happening is they come in and they have to add. Both those oxygens are coming from the osmium and stuff like that, or the permanganate, and so they have to come in, sort of the same way. The osmium can't come in and add to the other side. Okay, it has to come in from the same. Okay, it goes to the cyclic intermediate, and then when it releases, you're left with OHs on the other side. Now, usually the osmium, because it's expensive and more importantly, it's toxic. So like that, it's usually used catalytically and then regenerated. And here, this one uses peroxide. The other one that I've seen is morpholine oxide, stuff like that, so to regenerate. But that's not important. The big thing is when you see osmium tetroxide, what you're doing is you're taking a double bond, you're adding OHs across it. Okay, stuff like that. And so you'll see where this comes comes into play in a second. Okay, the last sort of general topic, okay, is going to be the cleavage of the of alkenes and alkynes. And so what ends up happening is, I'm going to draw it sort of like this. Okay, what you're going to end up doing is you're going to end up cleaving these. Okay, and stuff like that, and then swapping carbon-carbon bonds for carbon-oxygen bonds. Okay, and stuff like that. So for here, we'll talk about this. Right? So if you end up swapping carbon-carbon double bonds, your carbons are going to have two carbon-oxygen bonds on them. Okay, if you have an alkyne that you're cutting, you're going to end up with three carbon-oxygen bonds on each carbon. Okay, so with that, and so with the first one to talk about is ozone. Okay, so with that, and so this is going to end up cleaving here. Okay, and on a reductive workup, okay, so it's either dimethyl sulfide, which stinks, or zinc and acid. Okay, what you're going to do is again, you're going to slice these. Okay, but remember there's a hydrogen here, and just put oxygens on either side. So you're going to swap out carbon-carbon bonds for carbon-oxygen bonds. Okay, and so it's going to look like this, like that. Okay, and notice how there's a hydrogen here, so there's still that aldehyde remaining. And so if you were to stretch this out, it would look like this. Okay, under reductive workup, this isn't going to get oxidized further. However, with KMnO4, if you do this under warm conditions, under hot conditions, instead of doing that dihydroxylation, okay, you actually do get cleavage. But if you do the same reaction with KMnO4 hot, okay, usually under basic conditions, you're still going to get this this product here, but any aldehydes that are formed, okay, they are going to get further oxidized up to carboxylic acids. Okay, so it's going to be a very similar product. It actually does make this, but the KMnO4 is oxidative enough to come in and oxidize the aldehyde to the carboxylic acid. Okay, now if you do this under the ozone under oxidative conditions, okay, which is usually the workup is typically something like peroxide, stuff like that. So you would actually end up with this product here. Okay. Now another way that you can do this, okay, you can do this cleavage if you have OHs right next to each other that are pointing the same way. Okay, and how do you do that? The osmium. Okay, and stuff like that. And so what you end up doing is you end up cleaving between here and turning these CO bonds into C double bond O, right? So here, right? So with that, so you end up getting when you put it's either sodium periodate or periodic acid. It doesn't matter which. Okay, so with that, so again, you're going to be cleaving between those, right, and leave the aldehyde behind. Now the hydrogens go away, okay, stuff like that, and so you're doing the same thing here, but you can do it through a dihydroxylation, okay, and so you can run this, okay, so with that, and so you can turn a double bond into this by first doing the osmium, putting those hydroxylations on there, stuff like that, and so if you would take this and say do the osmium, okay. So like that, so the osmium reaction, like that. So put those on there. You can then cleave it with periodate. This is a very mild way of doing it. Okay. Now the groups have to be adjacent. One, the OH has to be adjacent to each other, and they have to point generally in the same way. Okay. And so here, that'd be better. You know. So notice how this one's pointed generally in the same direction. These two OHs. Stuff like that, and so you're going to get cleavage. Same thing here. You're going to say, wait a minute, one's up, one's down. Okay, that's normally a bad thing if it's axial. Okay, like this, if they're both axial. However, with just a regular carbon, regular cyclohexane, right, you can get you can chair flip. Okay, so these would chair flip into equatorial positions, right, and then that'd be close enough. Here in this fused ring system, okay, you can't get the chair flip, and so these OHs, you know, are too far apart for the periodate to grab them and stuff like that, and so the reaction the reaction doesn't occur. You know, because and if let's say this one here, right? So with that, so let's say this OH was over here, right? So with that, so you wouldn't get it either. They have to be on adjacent carbons. So for that, so for cleavage of alkynes, right? So you're trading 3 carbon bonds for 3 carbon oxygen bonds, right? So the way that we do that on each carbon is to make a carboxylic acid, right? There's 1, 2, 3 carbons. Doesn't matter if you use ozone, doesn't matter if you use peroxide. It's always going to end up with a carboxylic acid. Okay. So for that, and so to predict the products, right? So with that, so I'm going to sort of make this a little bit larger, okay? So with that, so we know there's going to be ozone, okay, and reductive workup, Okay, so you can go ahead and draw on that hydrogen there. Okay, and so we're going to cleave that there and put oxygens on either side. Okay, so you're going to end up with like that. Like that. I usually have them pointed together. Okay, so that's totally fine. Let's put that to draw them like that because it's a valid way of doing it, and it sort of helps to sort of see how they're put together. Okay, so for that same thing with this, right? Go ahead and put it in that hydrogen, but here you're going to put KMnO4, right? Under basic conditions and stuff like that, and so we are still going to cleave here. Okay, put oxygens on either side, but there's going to be an aldehyde here and stuff like that, so that's going to get transformed into a carboxylic acid. Okay, OH, like that. Now, one of the reasons why I do this, okay, is the classic problems are like if we had, say, this. Okay, and you said, okay, you did ozone under, well, ozone doesn't really matter. Let's say under reductive conditions or whatever it is. What was the original problem? Okay, this is a classic question on the on exams. What you can do is you can have those two carbonyls point towards each other. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Right. So with that, and so you can have here, right? So 1, 2, 1, 2, 3, right? Like this. Okay. So 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, and then have the carbonyls point towards each other. So this is where the alkyne originally existed. Okay, and so it must have looked like that. Okay, so 1, 2, 3, 4, 5, right? And where these two guys are pointed together, that's where the alkene should have been. Okay, there you go. Good job. Or good luck.